So in this video, we're going to be talking about oxidation reduction reactions. These are also called redox reactions, as well as the concept of oxidation numbers. So first we'll look at this reaction here. This is the oxidation of zinc to zinc oxide. So zinc reacts with oxygen gas to produce zinc oxide. And I've put here that zinc is oxidized and oxygen is reduced. So what does that mean? Well, one way of thinking about it is that, well, when something reacts with oxygen, it's oxidized, but chemists have a more general definition of oxidation. I've written that here, as well as reduction. So oxidation in a chemistry context is a loss of electrons, while reduction is a gain of electrons. So here, this zinc is actually, it loses 2 electrons to form the Zn2 plus ion. So you have 2 moles of zinc losing 2 electrons to form 2 moles of the Zn2 plus ion. And so these are the 2 electrons that it loses. And this loss of electrons is oxidation. While here, O2 gas it's going to be reduced. This zinc oxide is really Zn2 plus and O2 minus. So this oxygen is reduced here. So the half reaction for that is 1/2 O2 goes to 2 O2 minus. Remember, oxygen forms a 2 minus anion. And this is not 2, this is just 1. So I put 1/2 here to balance the equation. We have 1 oxygen on the plus, or here this is wrong. I should have said, I'll just write it here. 1/2 O2, this O2 gains 2 electrons to give you 2 O2 minus. So, again, I made a mistake. Okay. So the reason I have a 1/2 in front of this oxygen is so that this equation is balanced. You have 1 oxygen atom here on the right side, and you should have 1 on the left side. You have a -2 charge on the right side of the equation. So that means that this neutral oxygen molecule must gain 2 electrons, right? And so that's basically this reaction here is split up into 2 half reactions. This oxidation of zinc, so the loss of 2 electrons in zinc, and the gain of 2 electrons in oxygen. But really what happens here is these 2 electrons that are lost by zinc are the 2 electrons that are gained by this oxygen. So in effect, this neutral zinc here gives the electrons to the oxygen. And the half reaction for oxygen is shown here. It gives the electrons to the oxygen to form this O2 minus anion. And in doing so, turns into the Zn2 plus cation, or positive ion. So this zinc is oxidized, but it does the reducing. So it facilitates the gain in electrons for this oxygen. So whatever is oxidized is called the reducing agent. So I'm going to put here reducing agent. And whatever is reduced is pulling the electrons from what's oxidized. So oxygen is reduced, it's gaining the electrons, but it's taking away the electrons from zinc, right? So it is facilitating the oxidation of zinc. So we call it the oxidizing agent. All right. So that's a reaction with oxygen, but you can have oxidation reduction reactions without oxygen. And one example is the combining here, well, the reaction between sodium and chlorine to give you NaCl. So sodium has only one valence electron. So if you look at a periodic table, you'll see that sodium has one electron in its outer shell, while chlorine has 7. So what happens here is this sodium loses its electron in its outer shell, actually donates it to chlorine, and in doing so it becomes the Na plus anion, while chlorine, having gained an electron, becomes a Cl minus anion, and these two anions form a strong ionic bond. And this is another example of an oxidation reduction reaction. This sodium loses the electron here, so I should draw this as a solid bond here. This sodium loses the electron, so we say that it's oxidized, while the chlorine gains the electron, so we say it's reduced. But the element that's oxidized is actually doing the reducing, so it's facilitating the gain in electrons in the other atom, in this case chlorine. So sodium is the reducing agent, while chlorine, which is reduced, is facilitating the loss of electrons in sodium, so it's the oxidizing agent. So that seems easy enough, but what if we look at a more complicated reaction? So what if we look at this reaction here? Kind of running out of space, so I wrote the O3 here. But this reaction's a bit more complicated, and it's harder to tell. It's harder to tell which atoms are losing electrons and which ones are gaining electrons. So it's tougher to see which is being oxidized and which is being reduced. So chemists have actually made your job easier by developing a set of rules, which I'm going to write down here, which will help us figure out which atoms are being oxidized and which are being reduced. So let me scroll over here. I'll go ahead and write these rules. So these are rules for determining what's called oxidation numbers. So rules for, just write DET, determining oxidation numbers. Okay, so the first one, the oxidation number for a pure element is 0. So oxidation numbers for pure elements are 0. Number 2, the oxidation number for a monatomic ion, so say like the calcium 2+ ion, is equal to its charge. So the oxidation number for monatomic ion equal to its charge. And the example is calcium 2+, it has an oxidation number of 2. The third point, when fluorine is combined with other elements, its oxidation number is -1. Combined with other elements, its oxidation number is -1. I'm going to pause here, write down the rest of the rules, and I'll explain them right after. So I went ahead and rewrote the ones we did and added the others so that you can see them more clearly all together. So for pure elements, the oxidation number is 0. This is a 0, not an O, so that you can tell the difference. I put this slash through the 0 so you can tell the difference between it and the O in oxidation number. So for pure elements, say pure chlorine, the oxidation number is 0. For monatomic ions like Ca2+, we've already gone over this, but the oxidation number is equal to its charge. So Ca2+ has an oxidation number of 2. When fluorine is combined with other elements, the oxidation number of fluorine is -1. So in, say, lithium fluoride, the oxidation number of fluorine is -1, or in trifluoromethane, which is CHF3, the oxidation number in each fluorine would be -1. When oxygen is combined, and this is an O, not a 0. So this is a 0, has a slash through it. This is an O, does not have a slash through it. So when oxygen is combined with other elements, its oxidation number is -2, except for in the case of peroxides. Peroxides are compounds with the ion O2 2-. Typically you'll see an O2-, so oxygen would bear a -2 charge, but in this case, the diatomic oxygen, this polyatomic ion here, bears the -2 charge. So these are peroxides, and hydrogen peroxide is one example. Go ahead and erase this. So we'll have some space here. Okay, for hydrogen in a molecular compound or in a polyatomic ion, the oxidation number is +1. So, say in HCl, for example, the oxidation number of hydrogen is +1. And to find the oxidation numbers of elements not discussed in these 5 rules, you use rules 6 and 7. So use rules 6 and 7 when others are insufficient. And when we go over some examples, this will make sense. But I'll just state them for what they're worth. The sum of the oxidation numbers for an uncharged molecule is 0. The sum of oxidation numbers for a polyatomic ion is equivalent to its charge. So an example of this, a simple example of this one here, the sum of the oxidation numbers for a polyatomic ion. If you consider PO4, the phosphate ion, has an overall charge of 3-, and this is going to help us determine the oxidation number of phosphorus. So we know when oxygen is combined with other elements, except in the case of peroxides, that it's going to bear a -2 oxidation number. So each oxygen here is going to have a -2 oxidation number or oxidation state. You'll see both of those terms. So when you have 4 of them, that'll total to -8. 4 times -2. the sum of the oxidation numbers for this ion is equal to the charge, so it's going to be -3. So if you want all the oxidation numbers to add up to -3, this 3 minus might be confusing. That's one way of writing the charge. Some books you'll see -3 here instead of 3 minus, so I'll just write -3. So you want this to add up to -3, and phosphorus is going to have to be +5, right? Because +5 plus -8 gives you -3. So that's a simple example. What about an example that exploits this rule here? The sum of oxidation numbers for an uncharged molecule is 0. So if we look at N2O, this is nitrous oxide. We know the sum of the oxidation numbers here must be 0. So then this must be, well, we know oxygen is -2 because this is not a peroxide, right? So if the total is 0, we have 2 nitrogens, then each of these must be +1, which is +1. So we used the fact that we knew the oxidation number of oxygen, and we knew that the sum of oxidation numbers for this uncharged nitrous oxide is 0. So we were able to figure out the oxidation number for each nitrogen atom here in this molecule. One more example. I'm going to look at CF4. This is a tetra-substituted methane. And again, this is an uncharged molecule. So the sum of oxidation numbers must be 0. And we look at rule 3 here that says when fluorine is combined with other elements, its oxidation number is -1. So we have 4 of those, right? So 4 times -1 is -4. This all adds up to 0, so carbon has to be +4, has to have an oxidation number of +4. So hopefully that shows you how these oxidation numbers can be calculated. And this is going to be useful if we were to have a reaction, that's a bit more complicated than ones we took a look at. And I think I may have begun writing this, but I'm going to go ahead and write it again here. Six SiO2 plus 10 carbons gives you P4 plus 10 carbon monoxide molecules plus 6 CaSiO3. And here to figure out what's oxidized or reduced is a bit tougher, right? So these oxidation numbers will help us figure out what's oxidized or reduced. When we figure out after we figure out the oxidation numbers, which we're going to do here in a moment, the element that's oxidized is going to be the one with an increase in oxidation number, and the one that's reduced is going to be the one with a decrease in oxidation number. So let's look here. We know oxygen is going to have an oxidation number of -2, and we know this phosphorus PO4 has a -3 charge, so 4 times -2, we have 4 of these oxygens, will give us a total of -8. So 4 times -2 equals -8. This whole thing should be an 8 here. This whole thing must be -3, so this phosphorus must be +5. And we know that again, this is an ion, so this is calcium must be plus 2, right? We have 3 Ca2 plus cations and 2 PO43 minus anions. And this overall compound is this overall molecule is neutral, but it's an ionic molecule. So we figured out the oxidation state of this phosphorus atom here. Now let's look at this silicon dioxide. So we know oxygen, except in the case of peroxides, it's an oxidation number of -2. And we have 2 of them, so 2 times -2 equals -4. So this silicon must have an oxidation number of +4. Here we have pure elemental carbon. Remember, for pure elements, the oxidation number is 0. So I'm just going to put equal to 0. You have the same is the case here. This is another pure element. See, it may have 4 atoms for this P4 molecule, but it's pure phosphorus, so its oxidation number is nevertheless 0. So if you had something like O2, the oxidation number would still be 0. You only have the oxygen there. And that's that I guess that's where this rule here for pure elements, oxidation number 0, that overrides well this one, because where it says oxygen is combined with other elements, oxygen's oxidation number is -2 except for peroxides. Well, actually I shouldn't have said that, because in this case when you have O2, oxygen is not combined with other elements. When you have O2, oxygen is by itself. So really this rule number 4 doesn't apply, and it's rule number 1 that applies in the case of diatomic oxygen. But that's really an aside. That was just to say that just because you have 4 P's doesn't change anything as far as this rule applying. Okay, now to carbon monoxide. Oxygen's oxidation number, we know this is -2, therefore carbon must be +2, because this is an uncharged molecule. So the sum of the oxidation numbers must be 0. That is rule number 6 here. Now in this molecule, we know oxygen has an oxidation number of -2. We have 3 of them. 3 times -2 is -6. Okay, calcium. Calcium is always forms a +2 cation. So what must silicon be here? Well, these all have to add up to 0, right? So silicon here is negative. Is it? Well, let's see. Let me see. No, it's positive. Sorry, it's +4. +4. 2 plus 4 is 6. Minus 6 is 0. Okay, so now we look at which atoms end up changing their oxidation number. And if we look carefully through everything, we'll see that phosphorus, on the reactant side, it has an oxidation number of +5. And on the product side, has an oxidation number of 0. Then we look at carbon. On the reactant side, it has an oxidation number of 0. On the product side, it has an oxidation number of +2. So we see here that the oxidation number of phosphorus goes down from 5 to 0. So we know that phosphorus is reduced. So P is reduced. While the oxidation number of carbon goes up from 0 to +2. So carbon is oxidized. Remember, I didn't write this down and I should, so I will write it here. So the element whose oxidation number increases is oxidized, and the element whose oxidation number decreases is reduced. Should have written that earlier, but we can see that here in this example, that carbon's oxidation number goes up from 0 to +2. So carbon, we say carbon is oxidized. Again, that's consistent with this statement here. Alright, and the oxidation number of phosphorus goes down from +5 to 0. So it's reduced, and that's consistent with this statement here. And as I showed you with the two prior examples, the oxidation of zinc to zinc oxide and the oxidation of sodium by chlorine to form NaCl, whatever is reduced is the oxidizing agent. So phosphorus is the oxidizing agent. Well, carbon, it's oxidized, it's actually facilitating the reduction. So it is the reducing agent. If that's not clear, remember that oxidation is a loss of electrons and reduction is a gain of electrons. So when something is I got that back. This is reduction, right? So reduction is a gain of electrons, oxidation is a loss of electrons. So whatever is reduced and gains electrons, it had to have taken those electrons from something else, right? It had to make something else lose the electrons, and that something else would be oxidized. So what's reduced is called the oxidizing agent. This one facilitates, so what's reduced facilitates oxidation. So in this case, phosphorus, all right, phosphorus, it's reduced, but it facilitates oxidation. And what's reduced, or what's oxidized here, carbon is oxidized, its oxidation number goes up from 0 to +2. It's called a reducing agent because it facilitates reduction. So it's oxidized, facilitates, hopefully you can read that, facilitates reduction. And so carbon is oxidized, it loses electrons, but when it loses electrons, it gives those electrons to someone else, right? In this case, phosphorus. So in doing so, it facilitates reduction. Another way of thinking about this is just to realize that this phosphorus here, this oxidation state, you can think of it loosely as a charge. All right. So this phosphorus, in effect, I'm using the term charge in quotes because this phosphorus, let's say it's going from a +5 charge to a 0 charge. Well, it would have had to gain electrons to do that, right? Because it's bound to oxygen, and oxygen's really hogging its electrons. Remember, oxygen's very electronegative, and phosphorus is less electronegative than oxygen. Similarly, this carbon here is sitting by itself, all right, and it has an oxidation number of 0. But when it bonds to oxygen, oxygen's going to hog its electrons, and carbon's going to become more positive than it was. So in effect, carbon is losing electrons, so it's oxidized. But in losing those electrons, you can think of it like it giving electrons to whatever is being reduced, in this case phosphorus. So hopefully that sheds some light into oxidation reduction reactions, oxidation numbers as well. And these oxidation numbers, these are also called, aka oxidation states. So you'll also see that term. Perhaps your teacher uses this term and not oxidation numbers. Hopefully that was helpful.